Good morning. I'd like to welcome everyone to our technical seminar. Today's topic is equivalent visual flight deck technologies. I thought I would just spend a moment starting off this technical seminar by thanking everybody who has been participating in this series over the past, essentially since September of 2006. So it's been quite a while since we started these. And I thought I would just comment for those of you who've actually come to headquarters and come to the auditorium to hear the speakers, you may not get a sense of how widely watched and appreciated these seminars are, because when you stand up here, as I'm doing right now, you look out at an audience of less than 20 people. However, I know that there's a lot of you watching this out at the centers, and I also know there are a lot of people who download the podcasts after the fact. And in fact, I would just share with you that in the past 7 months, we've had over 34,000 hits on our website on the podcast downloadable format. And just in December, we had almost 6,800 hits. So these seminars are actually very popular. I think people are getting a lot of use out of them. And I know that Dr. Shin will continue them when he takes over as the AA on Monday. So for those of you who are interested in making sure that these sustain and continue, have no fear, they will. And you'll have lots more exciting talks to hear from in the future. I'm very pleased to introduce our two speakers today. First, Mr. Randy Bailey, as an Associate Principal Investigator for the Integrated Intelligent Flight Deck Project. He leads a group conducting research in crew vehicle interface technologies with the aim of reducing the propensity for pilot error, while at the same time minimizing the risk associated with pilot errors that may occur. Prior to his work with NASA, Mr. Bailey was the technical director of the Flight Research Group at the Calspan Corporation. His 20 years of work at Calspan involved research, development, test, and evaluation of flight control, flying qualities, and pilot vehicle interface technologies for advanced aircraft, including the development of head-up display standards for primary flight reference display and the design, development, and testing of a programmable helmet-mounted display system for an Air Force NF-16 aircraft. Mr. Bailey received a BS in Aerospace Engineering from the University of Virginia and an MS in Mechanical Engineering from the State University of New York in Buffalo. And our second speaker is Dr. Steve Young, and he is the principal investigator of the same project, the IIFD project as we call it, and he has been the PI since 2005. He leads a team of NASA industry and academic researchers and scientists who are working collaboratively in order to achieve the goal of overcoming flight deck-related safety barriers that would otherwise constrain future aerospace operations, such as those envisioned for the Next Generation Air Transportation System, or as we like to call it in ARMD, NextGen. Since 1993, Dr. Young has been a researcher at NASA in the field of avionics systems engineering as applied to low-visibility flight operations. His investigations have ranged from analytical studies to large-scale flight simulation and flight test experiments. Of particular note are his advancement of the idea of a monitoring capability that allows for the real-time validation of the geospatial models used by synthetic vision systems, and his work developing a runway incursion detection and alerting capability that provides direct warnings to pilots when these hazardous events become imminent during airport operations. Dr. Young has a BS in Electrical Engineering from West Virginia Institute of Technology, an MS in Electrical and Computer Science Engineering from Georgia Tech, and a PhD in Electrical Engineering, specializing in avionics systems engineering from Ohio University. He is an associate fellow of the AIAA and has authored more than 35 technical publications across a range of disciplines, including system engineering, navigation systems, remote sensing, safety critical avionics, and flight operations. And on a personal note, it gives me a lot of pleasure to be able to introduce Dr. Young, or Steve as I call him, because he's been with us from the very beginning. When I first started, my very first week, he was one of the first people to interact with me. He understood what I was trying to do in terms of restructuring the aeronautics program and focusing on long-term cutting-edge research. He jumped in with both feet. He took the challenge on. He helped to restructure this area of research. He has been dedicated to commitment to technical excellence. He is also dedicated to dissemination of research results, and for those of you who are interested, his particular website is excellent. I will say that's a standard which I'd like to see everybody emulate. And he's just a really good guy. So I'm very pleased that he's the last speaker that I will have the opportunity to hear and introduce. So with that, come on up, you guys. Thanks, Steve.
Thanks, Lisa. Good morning, everyone. Appreciate the opportunity to be here to talk about some of the research we're doing in aeronautics, in particular in the area of flight systems. I guess the first question one might have when you look at the title of our talk is, what do we mean by equivalent visual? It turns out that can mean a couple things depending on who you talk to. One group of people would say that equivalent visual has to do with providing the same flow rates in and out of airports regardless of the visibility condition, day, night, etc. Another group thinks of it in terms of visual cues that you might provide to the crew, trying to make an environment in the flight deck equivalent regardless of the visibility condition outside. Turns out these don't go hand in hand necessarily. You can perhaps come up with a way to do equivalent flow rates without having the equivalent visual cues in the cockpit. And conversely, you may be able to provide the visual cues in the cockpit but not get to this safely achieving equivalent flow rates. I do think ultimately, and the researchers that I work with think that ultimately it's probably going to be a combination of both, and we actually think we can do better than equivalent visual, but I'll leave that as kind of a teaser toward the end of the presentation. We'll talk about how we might do that. The last thing I want to mention up front is that there are a lot of researchers within NASA, across the NASA centers, that have been working this area. Randy and I are just two of those, and I just want to acknowledge all those other folks that have contributed to what you're about to see. Next chart. Randy and I will hit on 5 topics today. We've kind of split the talk into 3 thirds. The first third, we want to address history. We want to take a look back. What were the problems historically, and what are the possible solutions that we might think about to solving the problem? The second third, we want to get into some of the technical details, some of the issues that come up when you look at these various solutions, some of the studies we've done, and some of the findings that we've come up with based on experiments. We split that into avionics type issues and crew system interfaces. And then last third, we'll talk about the current focus, what we're doing most recently, and in the future that we see with regards to the research. Next slide. Again, let's take a look back. One of the pioneers in aviation, of course, was Charles Lindbergh. He wrote a great book called The Spirit of St. Louis that I can recommend to everyone to take a read. He writes about what it was like in the 20s to come up with the idea to fly transatlantic, to build the plane, and actually to do it. He actually flew over 30 hours in a very small airplane, below 10,000 feet, 100 knots. I mean, just an incredible accomplishment. And what he says in the book, which I think is telling, he says, why does flying have to be so dependent on the eyesight of the pilot? And then he answers his own question with a possible solution. He says, well, what I really need is a pair of spectacles to let me see through the fog. And then probably the most interesting truism, if you will, that he says is the next quote, which says that aviation will never amount to much until we free ourselves from the mists. Fortunately, Lindbergh's contemporaries took him seriously, and they probably also recognized this kind of truism. And so there's been a lot of development in the past 80 years to try to get us more free of the mists, if you will. And I'll highlight a few of those. Next chart. This is a snapshot of the flight deck of the Spirit of St. Louis back in the 20s. I think it was 1927 when he did his flight. Back then, navigation was dead reckoning. You used a timepiece, a compass, and a crude chart, and an estimate of airspeed, and then you would update that as you flew along. Basically, no one flew in low visibility or at night. You basically just stayed grounded because it was too dangerous. If you'll notice on this picture, I want to indicate one of the instruments is that T device there in the center. It was actually a way of indicating attitude using a bubble, like our bubble levels we use in our homes today. There was one for bank and one for pitch. So again, not much infrastructure to help Lindbergh back in his day. Now, if we move to the 60s, in that 40-year epic, we did a lot of innovations. A lot of technologies came along. We learned a lot about what procedures we should use in the flight deck, what training was needed in order to operate in low visibility or at night, which to me is kind of synonymous problem, a visibility problem. You notice that airplanes got bigger, they got faster. We had a very high target level of safety because we were flying a lot of the public around. So we wanted to reduce risk. So we actually went with 2 pilots. Actually, 3 crew members were in these planes. We had a navigator there in the back. The instrumentation moved from what you saw from Lindbergh. We had gyroscopes were developed for attitude, and a lot of round dials with indications of airspeed, attitude, etc. This airplane had auto land capability. We could land in pretty much any visibility condition using a radio beacon that was transmitted called ILS, Instrument Landing System. If the airport had that, then the airplane could land automatically, or the pilot could follow that guidance and land. So a lot of capability in that time frame. Radar, air traffic control, all these things came into play in this period. Next chart. In the last 40 years, basically what we've done is take a huge advantage of advances in digital avionics. We moved from an analog airplane to digital, and you see things like liquid crystal displays, CRTs, and there's head-up displays on this. This is actually the 787 cockpit that's coming out next year. So a lot of capability was added, and we got to the point pretty much where we are, you could argue, independent of visibility condition. We can fly in pretty much any visibility condition down to extremely low visibilities and land and take off. So we are capable, but there are a lot of caveats on this capability. You need to have a certain amount of infrastructure at the airport, a certain amount of infrastructure in the airplanes, training. You got to have a lot of training to be able to do this, and procedures have to be defined so we can do it safely. So next slide. Okay, let's zoom in a little bit on today's cockpit. They're called glass cockpits because of the predominance of glass, CRTs or LCDs. The primary instruments that pilots use are the primary flight display, it's called there, which is the blue over brown attitude indicator. Instead of having all the round dials, we've integrated information. We have airspeed and altitude also indicated on the same display there on the strips on the left and right. And then we have a horizontal situation indicator on the right, or more commonly called the navigation display, where you can see your flight path and how you're progressing along the path that you've input into something called the flight management system. If airplanes have head-up displays, some of them do, not many, but some do, and it's basically a repeater of the primary flight display, but it lets the pilot keep his eyes out at all times. Okay, next chart. So what's the problem? I put this chart in here to remind me I need to tell you what the problem is. It sounds like I've just told you, well, we're real capable, we can do this in any visibility. What's the real problem? Well, it turns out, like I said, there's a lot of constraints on doing this, and that's what we're trying to resolve in the research we do. Next chart. What is one of the effects? One of the effects is on capacity. As I mentioned, you need to have a lot of infrastructure at the airports to do this. You need to have an ILS system. You need to have lighting. A lot of approach lights, for example, have to be at the airport. These are expensive. You need to have procedures defined. It turns out there are a different set of rules for pilots to follow when they're operating in instrument conditions in bad weather. These are called instrument flight rules. So instead of using visual references, we use the instruments. And this is an example from Dr. John Hansman out of MIT, where he shows what happens at Boston when we go from VFR, the visual conditions, to IFR, which is the rules we have to follow in instruments. Turns out the capacity, what's on the left is arrivals per hour, and on the horizontal is departures per hour. And at Boston, the capacity is shown in blue, and then the actual arrival and departures are shown in the pink and black. And it turns out we go from about one arrival and one departure every minute to down around 40 every hour. 60 per hour down to about 40 per hour. And this is assuming, again, everyone's equipped, everyone's trained, and the airport has the ILS. There are about 5,000 airports in the U.S. Only about 1,000 have runways that have at least one runway that has ILS, and only about 100 will go down to what we call Category 3, which is visibility conditions less than 700 feet. So we definitely, a lot of airports have to close when we go to instrument conditions. Next chart. There's also an impact on flight safety. What I'm showing here is some data on small aircraft, because one of the common things that happen with small aircraft is the pilots are trained by VFR, but they occasionally or frequently inadvertently get into IMC conditions, bad weather, and they're not trained to get out. And so you see a lot of, over 50% of the accidents in this study happen due to that fact, where we're getting into IMC, low visibility, clouds, night, and we have an accident because we're not, in most cases, not properly trained or equipped. Next chart. And then there's the future to think about. That as Lisa mentioned, there's something called the Next Generation Air Transportation System that's being defined. It's being designed now, and people are planning about how to implement it and pull it off. One thing they talk about is we need to be able to get to the capability where we can support 3 times the capacity that we currently support. And one way to do that is to provide more capacity in IMC in bad weather. They call this equivalent visual operations, and they're primarily referring to the ability to have equivalent flow rates, not necessarily equivalent visual cues. The next challenge is a military challenge. They're facing things like brownout, it's called, where the dust blows up to the rotorcraft, and these helicopters can't land or maneuver or take off when they get in this brownout condition. And they also have the issue of getting in and out of airports with cargo or troops, where the airfield's not equipped with any landing lights or any approach landing system. So that's a problem. And then let me move to the next. Supersonic transports. The designers of these future vehicles would like to be able to consider windowless cockpits to help with the aerodynamic design of space. So we're looking at that as well as a future challenge where you really have no visibility. And then the last challenge really has to go with our exploration initiatives. As we go to the moon, the Mars, and beyond, again, cloud and fog may not be an issue, but there's long periods of darkness. And we'd like to be able to do reconnaissance flights, low-level surveillance flights, if you will, maybe with UAVs. And you want to have situational awareness for the operators of these vehicles to see what's out there. Okay, next chart. So what are a few possible solutions? Well, one is automation. You know, some people say, well, let's just automate everything, right? Okay, that's possible. But I would argue that even if you automate everything, whoever is ultimately the ultimate authority, there's always going to be a human in the loop at some point, and we need to keep them fully engaged with what's going on, what's the environment we're flying in. So even in fully automated, I would argue that you need some situational awareness information to provide it back to the crew about the external environment. The latter four I'll talk about in a little more detail, which is providing enhanced cues to the crew. Okay, next chart. The first one is enhanced vision. Enhanced vision is really kind of today's solution to what Lindbergh was talking about back in the 20s. You know, can we provide some spectacles to see through the fog? Well, this is using advanced sensor technology that can see better than the human eye in some conditions, in some atmospheric conditions. This example is a forward-looking infrared detector. It's mounted in the nose through this little window. The camera's looking out, and it provides a video image of what the infrared thermal sensor is seeing. And it's very good at night, and Randy will show some images of this and talks about some of the limitations of FLIR. And there's some other sensors that can do this as well. But enhanced vision, in terms of a definition, is basically using sensors to try to see through the fog. Next shot. Synthetic vision is a completely different take on this. What we want to do is remove the obscuration. Instead of seeing through the fog, we just basically remove it. We model everything, and we present these models from the perspective of the pilot flying. So in this case, we've put it on a primary flight display with the attitude information overlaid on things like terrain, man-made obstacles, airport features like runways, etc. So again, it's a complementary idea with a different set of issues that you have to think about. Next chart. And here's just a couple snapshots to show what this might look like. One, the top is out the window at night. You see the lights. But imagine if there were no lights at the airport. What would that look like? It'd be all black, right? So the images on the bottom two would be supplemental information that the crew could use if the airfield didn't have lights. The one on the left, the EV, is again shown in pretty much a pristine condition, and that is in night conditions. The FLIR is very good at night, but as Randy will talk to, when you get heavy rain or other obscurations, it's not always as good as this picture might let you believe. And then the synthetic environment, it's always going to be a blue sky or whatever we create. You know, it's going to be clear weather. It's completely independent of weather. But of course, it has its limitations too. For example, in this picture, there's actually an airplane down near the end of the runway, and that's not shown on the synthetic environment unless we have some way of bringing in that information and superimposing it. And I'll talk about that later. Next chart. Now I'd like to get into some of the more interesting stuff in terms of a researcher, some of the issues and studies that we've done. I'm going to talk about the avionics systems work, at least highlight some of it, and then Randy will come up and talk about the crew systems work and finish this out. Next chart. Okay, so what does a synthetic vision system look like in terms of avionics? Well, you need, of course, you need some indication of position. Where are we in space, three-dimensional space? We need the attitude. We need some other information about the aircraft state, and we get that from like the inertial platform that's on board, or perhaps GPS if you have that. So that would be one input. Then you need models of the geospatial features, the terrain, obviously. You also need models of the airport features, runways, taxiways, even gate locations. We can model all of these things. Since they don't move very often, we don't really have to update these models very often. Obstacle information, man-made towers, tall buildings, we model those as well. Flight path data, these are the published flight paths that we're allowed to fly, highways, if you will, that the pilots can fly through. And then some folks have talked about superimposing imagery on top of this to give you things like cultural features, rivers, highways, things like that. We can definitely do that. So then you have a smart or a computational facility that will integrate all this and project it on some sort of display. And this is kind of analogous to what you have in your cars today with the GPS navigators, right? That's really kind of a synthetic vision system, superimposing your own position onto a model or a database. Next chart. One of the issues that has been a difficult one, or one we have to think about when we do this synthetic vision environment, is the quality of the models. How good do they need to be? How good can we make them? Well, it turns out remote sensing technology is really just amazing. We flew a shuttle mission back in, I think it was 2001, where we mapped the entire surface of the Earth between plus and minus 60 degrees to a 30-meter resolution. So we have practically the entire Earth mapped out to this 30-meter post spacing. And if you want more than that, you can use airborne laser scanning technology, which can map down to the centimeter level. The picture on the upper right is actually a model. It's called a geotiff. Every pixel has a 3D coordinate, latitude, longitude, and elevation, down to centimeters. So extremely accurate, almost looks like a photo. The question that we come to is, if you can go to the next transition, how good does it need to be? We need this to be useful, but if we make it too compelling, if you will, it can be misused. For example, if you were to fly using the display there on the bottom right, the model, if you will, of New York, you might think you could fly down the streets of New York and not have a problem. Whereas we haven't modeled for things like transmission lines, right? We may not have modeled guy wires and other things. So it might not be a wise thing to do. So there's kind of a trade-off we have to do with respect to how good does it have to be. Next chart. A related issue has to do with integrity, and this is probably the most challenging issue we've had to face in terms of avionics systems. Pilots are taught from the beginning to trust your instruments, right? When you're in low visibility, when you can't see out the window, trust your instruments. So we need to be able to provide that trust through the avionics. And it's tough to do in terms of the models. The models are created, and it's hard to know because time passes. Things do change. So we have three types of integrity that we worry about, or that we've decomposed this problem into. One is data processing integrity. From the time that we collect the data until it's actually put on the avionics system, what's the probability that the data has been corrupted or altered? We need to be able to track that, quantify it, and be aware of it. And there are ways to do that we've reported out. The second problem is what we call data system integrity, which really has to do with something like software integrity. What is the probability that a single error, once we get it in the avionics system, that a single data error will lead to an accident, will cause an accident? And you might say, well, that's pretty unlikely, but there are certain points in this model that it might be if you use them in the wrong way. For example, a threshold point. If you're going to try to fly to a threshold point that's been recorded, if that threshold point's wrong, there could be a fatal accident, for example. And so we've also done some work on that one. But probably the culmination of this is another type of integrity called the operational system integrity. And this has to do with really the operational domain. What's the probability that this system will provide misleading information to the crew? So that, they think you're flying to the runway, but maybe the runway's actually over to the left or over to the right. And you're just going to fly it on down like everything's great. This is a difficult one because it's context specific. You need to know something about real-time measurements. Okay, next chart. And this is just an example that kind of highlights what I'm talking about. One definition of this operational integrity is the ability to be able to provide alerts, timely alerts, when the system should not be used for its intended function. And there are different types of intended functions you might imagine for SV. The one on the left is where I'm going to use this for my sole means to land the airplane. Okay, that's a different intended function from on the right, where it's just an indication of terrain above me, terrain below me, and just what they call situational awareness information, not to be used for navigation. Next chart. So this led us to start thinking about integrating SV with EV, because they are complementary, and we can get the real-time information from the enhanced vision sensors. So if you'll next chart. Again, what we want to do is to bring in some sensor measurements. It's almost like if you're in a dark room, you may have a mental model of how to leave the room, right? But most of us would still put our hands out and make some measurements, right, to make sure that we're kind of in the right ballpark. So that's what we use the EV sensors for. We make some measurements to confirm the validity of our models, and also to detect objects that we may not have modeled. And in this example, we show a runway incursion detection. Traffic is detected using a sensor. We alert the pilot on an overlay. Next chart. The issue of real-time validation. I mentioned the problem of system or overall system integrity has a lot to do with operational context. Where are we in the flight? What are we trying to do? It's hard to presuppose all the possibilities, all the possible contexts we might be in. So what we proposed and what we studied for a while was, how would you make some real-time measurements so that you can let the pilot know in near real time, what is the quality of the model right now based on your context. And you can use the various sensors to try to do this. The nice thing about it is you can use statistical detection theory to bound your integrity. If we know a priori all the statistical parameters of the inputs, we can come up with an overbound of both the measurement side and the modeled side of what the errors should be. We can, using this method that we came up with, you can a priori pick the probability of false alarm that you're shooting toward, the probability of misdetection, which is really our integrity value, and you can pick the minimum detectable error that you want to detect. All these things can be put into the design a priori, and you can come out with specs for the type of sensor that you need and the type of model that you need. Okay, next chart. And we tested this approach using various sensors to kind of give us a sanity check, and it turns out you can do it with off-the-shelf sensors to varying degrees. The one on the left is a radar altimeter approach. The radar altimeter is available on most airplanes, many airplanes, and if you have that, again, it's making a measurement looking down of where the ground is, your height above the ground. And what's shown in these plots are our agreement statistic, T, as a function of when we start injecting errors into the models. And per our hypothesis, in this particular case, we designed the monitor to detect a 35-meter error. And as we start injecting errors, indeed, once we got to 35 meters of error, all the observations showed us exceeding the threshold, and so we were getting alerts. So we did achieve our desired integrity. On the right is using an X-band radar, which is looking forward to see features in terrain features using the radar, and a similar kind of approach. We have a slightly different agreement metric for T, but again, we can detect errors, which are the blue lines here. As we inject more air, it becomes easier and easier to detect them. The bottom right is a newer technology. We're not quite as far along with this, but it's the idea of using GPS. It turns out there are ways to detect the specular reflections of GPS signals that come from satellites. These signals bounce off the ground, and if we can observe where those reflections occur, we've got another way of seeing where the terrain model is, and we can compare that with our onboard model. And so far, we show good agreement between these two approaches. One more chart. Last thing I want to say about avionics systems is this function that could automatically detect runway incursions. Randy will talk about a way how you could do it with a pilot observing traffic on for example, a cockpit display of traffic information that is overlaying on a runway environment. You can let the pilot do the detection, but you could also have an automatic function that the avionics can provide, where if we know where the traffic is, and we know where the airport runway is, and we know where we are, we can automatically detect these incursions and alert the pilot. And this is an example presentation on a HUD, and we've done several flight test experiments using something we call the runway safety monitor that shows that even for this experimental system, our probability of misdetection and false alarm was down around the 10% error rate, which is a nominal acceptance rate to the pilots. And so with that, next chart. I think at this point I'll hand it over to Randy to talk about some of the cruise system interface issues. Thanks.
Good afternoon. As Steve said, I'm going to talk a little bit more about the technology, and more importantly, I'm going to talk about how this technology manifests itself within the flight deck. Next slide, please. I'm going to touch again a little bit in terms of the synthetic and enhanced vision technologies, and then how this all boils together into what we call equivalent visual technologies. The concept really is shown here on the left, or on the slide, for our enhanced vision system. The upper left-hand corner shows you an out-the-window view of an approach to an airport. It's at night, obviously, so the only features you can see are that which is illuminated by lights. That's your natural vision, and it obviously has some severe limitations at night. If it doesn't have a light on it, you're not going to see it. On the other hand, enhanced vision on the lower right-hand side, you can clearly see shows orders of magnitude improvement in what your natural vision can provide. What you're seeing in the enhanced vision system is from a sensor called a forward-looking infrared. So what you're actually seeing is the temperature differences in the environment. So you can see roads, you can see some of the streams as we go into Wallops Flight Facility, you can clearly see the runway information. So what you're seeing is the temperature differences in the cultural features, in the objects out in the environment. FLIR, again, can provide orders of magnitude improvement in certain conditions, but it's important to understand two of its limitations. The first is the fact that what you're seeing, again, is temperature differences. So it's a matter of what the temperature of the target is versus what the temperature of the background is. So if you were to be standing behind something that would happen to be the same temperature you are, you would actually be invisible. You wouldn't be able to see it. You also get into the fact that it's a function of what the atmosphere is between the sensor and the object. So as you can see in this picture, you can actually see some of the clouds in the background. So FLIR does not necessarily guarantee that you will see through all atmospheric conditions. In fact, no EVS system can guarantee that it will see through every atmospheric condition. So there are weather issues that you have to worry about. The other limitations with this type of technology is training. The flight crew that's flying the airplanes do not necessarily have a master's degree, a PhD in sensor phenomenology and physics. In fact, they may be music majors, for instance. Not to pick on music majors, but the idea is there's no requirement for education to become a pilot. So what you're now going to have to do is to train the pilots, no matter what their background is, to understand the sensor phenomenology. And that can be a significant limitation. It can happen, it's doable, but it's, again, one of the limitations. Next slide, please. What I'm going to show you here is the contrast to that, and that's synthetic vision. As we said, it's a virtual world. The key to synthetic vision is the fact that it is almost a natural presentation to somebody who flies an airplane. It's almost like day VFR, visual flight rules in the cockpit. If you're a pilot, you can almost immediately understand this presentation and become assimilated to the environment in terms of where the terrain is, where the obstacles are. So it's very easy to understand. I'm going to run the video here, if we will, and we'll show you how this looks in real time. It's a video presentation, but nonetheless, we'll go through some of the characteristics of it. But again, it's a computer-generated presentation based upon an onboard database and a real-time navigation system. Our research shows that, again, it provides an amazing improvement in terms of situational awareness for the pilot. They understand where the terrain is. They understand where the obstacles are because we provide this intuitive display in the cockpit. We can give them guidance information. We can give them explicit depictions of where they need to fly by the tunnel information, which I'll talk about in just a second. So again, it's a way to provide some very intuitive and obvious information for the flight crew that they don't have with today's technology, and we want to provide this information to them. And it provides, again, one of the key factors is not only its ease of understanding the information, but it's an integration concept in terms of it gives us a capability where we can integrate a vast amount of information in a very intuitive way to the flight crew. The cool thing about this technology is the fact that when you look at enhanced vision and you look at synthetic vision, they both have obvious advantages and disadvantages. And it turns out that the advantages of one are the disadvantages of the other. So they're very complementary technologies from the standpoint of if we can combine those two technologies smartly, we can create something that as a whole is better than each singular part. And that's the whole concept of an equivalent visual technology. We can go to the next slide, please. I'll talk a little bit about how these things are built so that you can understand how we've done the research and where we're going with respect to equivalent visual technology. It shows you a test that we did in terms of trying to define what synthetic vision should look like. Again, as Steve said, synthetic vision is a database. The database is basically latitude, longitude, and elevation points scattered about where you're going to fly. You can take those points and you can draw a line in between each one of those points and you get what we call a wireframe, which would be the center top figure up in that upper left-hand corner. So that would be a wireframe depiction. It works, but it's not necessarily very pretty. On the other hand, we could color the terrain using elevation color coding, so we could accentuate different altitudes. We could color it plainly. We could use contours, like a contour map that you might see. We could even put aerial photography, where we could actually use aerial photography and drape it on top of that database. So many methods we could do in order to provide that. And so we obviously had to develop some research that said what is the necessary, what's required, where do the goods and the bads of these techniques lie. So we did a series of research studies, and this is just one of them as an illustration. But this shows you a comparison where we gave the pilots this canyon view, if you will, where there's a distinct valley in the synthetic vision data. And we said, fly as well as you could, following the contours of the valley, without any guidance information, so it's just flying with reference to that database. So fly as well as you could along the contours of the valley, maintaining a constant altitude. And we gave them those different presentation methods. We actually varied the integrity, or not the integrity, but the accuracy of the database, that DEM resolution chart on the lower right, and we tested to see how well they could do. And the results are shown in the two graphs, showing cross-track error. Cross-track error is how far off they were in terms of flying along that valley. As you can see, the checkerboard, the elevation, the photorealistic provided the lowest cross-track error, meaning that the pilots were most accurately flying along the valley. They could best see from that presentation where the valley was and to maintain their position along that valley. So those provided the most information for the pilots as they flew that, as far as the terrain information. So that's goodness. Obviously, somewhat obviously, as you could well imagine from the chart Steve showed before, the higher resolution, that is where you have more information in that database presentation, the better. So as you get more resolution in the DEM, the pilots are better able to tell the features of the terrain. Next slide, please. As I said, synthetic vision provides an integrating concept. Not only do we provide information about the terrain, we can also provide information about where the pilots need to fly. So we're providing information that the flight crew now gets from various displays. We can put that on one. And this is an artist's rendition of what a highway in the sky might look like, where we're doing a circling approach into a runway in the mountains in Colorado. Next slide, please. To show that same kind of concept on synthetic vision, we provide a head-down display of the terrain information and then can provide any different ways of depicting the tunnel path. And there have been many ways that we've researched, whether they're full tunnels, whether they're just little corner posts of the tunnel, or whether they're more dynamic depictions of the path. But the key element, again, is the integration of providing explicit terrain and path information on the same display, so it's almost unambiguous as far as where the pilots need to fly with respect to the terrain and the obstacles, so they're aware at all times of that information. Next slide, please. Here kind of shows you a quick summary of the results in terms of providing the tunnel information and not providing the tunnel information, and the key facet in terms of what the tunnel provides you. It shows you RMS errors in terms of the pilot's ability to fly a path, both laterally and vertically. Shows you when we show a tunnel and when we don't show a tunnel information. And the key change between these two data points, if you will, are the lateral errors. When we give a tunnel presentation to the pilots, they are more able and more accurately able to fly the tunnel path laterally in terms of they know where the turns are coming. So the pilots have less workload because they are fully aware that the turn is coming up. They have better situation, they know when the turn is coming up, and they have better performance because they know when the turn is coming up, so they can better execute that turn, they can better fly that turn. It's called basically preview. They know the turn is coming, so they're aware of it, as opposed to without the tunnel, they don't have that preview, and they're more in a reactive mode. So again, situational awareness is understanding and being aware of what's going to happen, so they're ahead of the game. The key element, again, of this is the performance. we get performance on the order of what we call flight technical error. That is the contribution of the pilot in terms of flying the airplane. We get flight technical error as low as 0.05 nautical miles and almost down to 0.02 nautical miles. As we move into a performance-based air traffic system where we start talking about required navigation performance, or we start talking about required performance of the vehicle, we have to include the flight crew in that performance. And with these technologies, we can minimize the contribution of the flight crew in terms of if they're manually flying these vehicles, we can make it so that the performance of the total vehicle and the pilot is as low as with automation as without. So again, it's a matter of improving the situation awareness as well as improving the performance of the total vehicle. Next, please. I'm going to go through a little bit in terms of how this information manifests itself into the cockpit. Again, trying to use one study to illustrate how we did that and how we're building this equivalent visual capability. We did a study of looking at various presentation methods in the cockpit and had a series of pilots fly different various configurations. The first chart shows you the concept of having a very large instrument panel showing a visual camera view out the window and then having insets, if you will, of enhanced vision systems. So we've got the real world in a visual camera with an enhanced vision system inset, with and without fog. So if you hit the next transition, please, you'll see that in the fog, you can't see with the visual camera, so the pilots had to rely on the enhanced vision system. In the case that we simulated, the enhanced vision system actually could penetrate the weather that we provided, so it was an ideal EVS if you want to think of it that way, but we wanted to test, again, an EVS that is weather independent from this scenario. Safety is not a matter of typically just the nominal system. One of the important facets of safety, doing a real safety evaluation, is the off-nominals, the non-normals. What happens if something doesn't work right, and what's the reaction of the flight crew to a non-normal situation and how they cope with that situation. So one of the key facets in our testing is the introduction of these non-normals. In this case, we introduced two non-normals. One is a navigation error. For instance, an ILS system was out of service, or an ILS was off of its expected course. It had a bend in the ILS, for instance. And the other one was runway incursions. Again, for some reason, a piece of traffic, a truck, whatever the case may be, was on the runway when it shouldn't have been, and the flight crew wasn't aware of that scenario. So we tested these unexpectedly. We didn't tell the flight crew these things were going to happen, and we wanted to see what their reaction was with these concepts. As you can see here, 98% of the time, the pilots in this configuration saw the abnormal navigation system, but there was a 2.1% case where they didn't see the abnormal navigation error. 4.2, they didn't see the runway incursion. So typically, that's pretty good. They did a fairly good job in terms of picking up those abnormals. Next transition, please. If we did the same type of test with a different system, this time using synthetic and enhanced vision, where this is a database presentation on that large view, not a visual camera, and EVS insets, you can see the missed non-normals went up significantly, and almost to the fact of unacceptably, in terms of the fact that the pilots weren't able to use effectively synthetic and enhanced vision in this manifestation effectively, so that they had a much higher rate of missing the navigation errors or missing the runway incursions. Not something that we wanted to see with this technology. Next transition, please. However, if we take the same depiction that we had before, but this time in the background, behind the glasses, we like to say, this time if we had these decision aids, these image processing algorithms that we're using to automatically help the pilot do runway incursion detection or to do database integrity monitoring, now you can see that we've gone to the case where they don't miss any of the abnormals, the non-normals that occurred. Now, we didn't test the fact that the decisions aids may in fact themselves have missed alerts or missed scenarios or false detections. We didn't test that in this scenario, but it illustrates where we need to go with this technology in terms of we need to provide the information to the flight crew as well as helping the flight crew by having automatic algorithms and flight critical avionics providing a lot of the integrity and accuracy checks. Next slide, please. So again, we need both of those capabilities, both automatic and manual detection. We need the flight crew to be fully engaged in what they're doing to most effectively use all the information. Many ways we can do that. We've got a slew of research that are looking at the different ways. You can do things like spatial separation, basically providing the pieces of information on different displays. In this case, the flight crew, if you will, has to blend two pieces of information into one mental model as they use that information. So they're looking across two different displays and again, trying to build that best of both worlds, trying to extract the goodness out of the enhanced vision, the goodness out of the synthetic vision to build the best of both worlds. Another way to do it would be to provide that same information on the same display. That can be effective. However, now we get into one of the issues, what we call clutter, in terms of too much information on one display that makes it more difficult for the flight crew to understand it. They have some struggles trying to understand the different pieces of information. And we want to make sure that not only do they get the information, but they need to get it efficiently. And then lastly, we can obviously fuse the information using image processing algorithms. We can go through and we can use an algorithm behind the glass again to try to bring that best of both worlds. That is technology that we are working on. We still are working on it because we're not there yet. We know a lot of the goods in terms of how to do it, but we don't know all the answers because it's not a trivial problem at all. One of the key elements that we need to do as we do this fusion, again, is understanding what pieces of information the flight crew needs and how to make sure we maintain that as we do the fusion. Next slide, please. I'm going to go through and talk about a little bit about where we are today and then go in about where we are tomorrow with this technology. Enhanced Vision System today provides what we call an operational credit. The FAA has just revised their rulemaking such that people that operate an approved enhanced vision device on their airplanes, shown on their head-up displays, can now proceed on an instrument flight, on an instrument approach, can now descend below the published decision height as long as they have an enhanced vision system operating on their airplane, and they can see the required visual references to the runway. So what we're showing here is a depiction of how we have, or some of the research that has led to, if you will, an optimal presentation for the pilot flying using this type of capability, where we have an enhanced vision system which needs to be on and operating as we approach the decision height, shown there in the lower left-hand corner, so that if the pilots can see the required visual references, they can continue below that decision height and then safely land on the runway. But again, because the enhanced vision system is not weather immune, that weather may affect the characteristics of that, what you see is synthetic vision is optimally provided for the pilot flying above a certain altitude. From the standpoint of synthetic vision, when you're up and away and flying, is weather independent. So you provide the pilots that intuitive and obvious information of where the terrain, where the obstacles are, where the flight path is, to get you set up to the point where you can then use the enhanced vision system effectively. And we use what we call transition phase to provide visual momentum. The concept of trying to take information again from one and carrying it through to the next presentation to try to improve the pilot's ability to keep that key information from the one and transition into the next one smoothly, to make sure that the pilots are always in the loop and always able to maintain their awareness of that information. Next slide, please. I'm going to show you a video of what this looks like. It's a quad view, so the upper left-hand corner is going to show you the head-up display, showing you that transition from synthetic to enhanced. The lower left-hand view is going to be an attitude indicator, so it shows you their head-down display, and the lower right is a cockpit view, showing you an over-shoulder view of it. And the display on the right, upper right, is the pilot not flying. It's a two-crew cockpit, so the pilot on the left is flying the head-up display, showing you that information. The pilot on the right is flying and using the pilot not flying display. And one of the things we found in our research is for the pilot not flying, who's not actively controlling the vehicle, it's best for them to be able to have both synthetic and enhanced vision in a way to manipulate the two so that they can best extract the information manually, doing it that way, rather than for the pilot, there needs to be an automatic transition. If you can run the video, please, we'll show you what we mean by this. We're doing an approach to the runway. You can see it on the upper hand left on the head-up display. If it runs. Here we go. So you'll see the upper hand left-hand corner is going to transition from synthetic to enhanced. Again, we're trying to keep visual momentum, so you'll see some features of that display are retained. And now we've gone to the sensor view in the upper left. You can see on the upper right now, the pilot not flying is going to be toggling back between synthetic and enhanced, trying to get different elements of information that they both provide so that they can best understand a lot of the scenarios that are going on. On the next chart, I'm going to talk about some of the results and how these things have changed in terms of the pilot's ability to detect non-normals and really unexpected events now that we've progressed along in our research. The results have shown that, again, I showed you that previous study looking at those non-normal events. This is what one of the non-normal events look like as we've hopefully optimized the presentations for the flight crew at this point in time in our research, where for the pilot flying now, you can see a depiction of enhanced vision in the background, and the synthetic vision component that we've retained is just the runway outline. So we don't overwhelm them with a database presentation. We really give them the database information that's most relevant to them, and that's the runway. And when we have navigation errors, non-normals, if you will, things that shouldn't happen but sometimes may, when we have those non-normals like this, the flight crew's ability to handle those non-normals has been significantly improved. So much so that in this experiment, we had no pilots have an error or have a misinterpretation of this image. They all recognized the non-normal and navigation error and all successfully landed the airplane. Next slide, please. When we gave runway incursions, and it's hard to see this on this projector, but there is actually a fire truck located about 1,000 feet down from the threshold in low visibility conditions. In this scenario, again, we were able to, just using the flight deck information and these optimized techniques, we were much better able to combat these unexpected events with this kind of technology. For the pilot flying, it's a difficult problem to still see the runway incursion in this case because the pilot is very engaged in flying the airplane. The symbology that the pilot uses sometimes overlays the vehicle, but it's still something that is useful and is better than not having enhanced vision system. But the key factor is the pilot not flying. He's the one that has the duty and now has the information within the cockpit to have the best ability to find an unexpected non-normal event, in particular a runway incursion of this type. Next slide. So where we are today, we have about 600 airplanes flying in the National Airspace System with enhanced vision systems. That number is growing rapidly. This shows you a state-of-the-art flight deck as it is today. Synthetic vision has started in the inroads in terms of general aviation, trying to provide situational awareness and mitigating, as Steve said, that inadvertent flight into VFR or into instrument conditions. So now they have a safety benefit from synthetic vision. We're now moving synthetic vision from that general aviation up into the business aircraft and moving on. Enhanced vision went to the business aircraft and is going in both directions. So this technology is here today, but it is of limited, let's say, operational benefit at this point in time, because what we need to do is we need to be able to provide the integrity and the accuracy and the reliability of these systems in order to use it effectively, again, to do something with this vehicle, with this equipment that we can't do today. And that's one of our challenges as we move forward that I'll talk about. But the technology is there and it is moving forward. One of the key elements is some of the activities that we're doing, not only in research, but also trying to do collaboratively as far as rulemaking. We're starting to work with the FAA. They're very proactive in terms of this technology and its ultimate benefit. So we're starting to put together requirements on how we can use this technology to actually go to what we call 0-0, all-weather landing capability with this type of equipage, and how we can do that under the RTCA umbrella of trying to provide a minimum aviation system performance standards for it. Next slide, please. So our future implications of this technology, again, is the concept of an equivalent visual operations. The technology's there. It's a matter of developing the flight critical avionics functions to do it and making sure we do it right. We'll obviously always have the role of automation and the role of the human in that, so we're trying to make sure that that is optimized. A key concept in the next-gen environment is shared situation awareness. The idea of every airplane is going to be, and every ground station, if you will, is going to be part of this net-centric environment where information from one is going to be able to be shared. This is going to be a significant amount of data that's going to have to be passed around. But the key is for the human on the flight deck to be able to get this information in a form that they can effectively use. And these equivalent visual technologies, we think, are one of the key attributes for trying to handle that information effectively and intuitively in a way that the pilots can effectively use it. Next slide, please. This gives you a kind of an overview, again, of some of the research we're doing and how we can do it from the standpoint of trying to provide display media as well as the information in a full field of regard. Remember that synthetic vision and enhanced vision is not necessarily just focused in a small part of space in front of the airplane. It actually can encompass the entire airplane. So we need to be able to provide a way, and we use these head-worn displays, for instance, as a method that we can provide this information in a spatial location. So in other words, if there's information from an airplane off to our left-hand side, and we want to be able to most intuitively understand who's giving us that information, it's not to go head down in front of us and look at a display. It's to actually put the information over to the left-hand side. And that way the pilots are best understanding of the information as well as its impact or potential impact it may have on our flight. Next slide. So our current focus, again, is this equivalent visual capability. As Steve said, equivalent visual operations may have different connotations to different people. For us, it's a matter of trying to provide if you will, an electronic way of creating visual flight capabilities, but that's not all we want to do. We can do better than just visual flight. We want to be able to show things that the pilots actually can't see with their natural vision. For instance, clear air turbulence. You obviously can't see that with your eye, but we have sensors, hopefully, that will be able to provide that information onto the flight crew and provide that on these types of displays. Actually showing no-fly zones, restricted areas, dynamic events such as closed runways if they occur, notices to airmen as information airspace changes are dynamically made. We've got a way in order to provide that information in an intuitively obvious and in a better way of doing it to the flight crew rather than just some of the ways that are out there at this point in time. Aircraft intent is another key factor in terms of if you are flying VFR and you're told to follow an airplane, you don't necessarily know what that airplane in front of you is going to do, but what they do can make a significant impact on how you react to what they're doing, how you know. Again, it's a preview situation. If we can show on these displays aircraft intent in an intuitive fashion, we can better load the flight crew that's following that airplane to anticipate changes, non-normals, that kind of thing, improving the safety and the operational flexibility that we have. And obviously, under the flight deck program, we need to do this in a standpoint of developing design methods and goals that enable the human contribution to safety and performance to be understood, quantified, and applied. Next slide, please. Hopefully, we're providing technology and methodologies and research where we can finally free ourselves from the myths to finally realize Lindbergh's dream. We are trying to provide R&D towards that equivalent vision capability and beyond. As Lisa said, I think we have an excellent website that's got a wealth of information. Here's the links to that website. So please go to it and see some of the research, which Steve and I were just ever so briefly able to talk about some of it. And then finally, I want to show you a video. Next slide. This video is actually from STS-115. And this is, if you will, if we could put synthetic vision on the shuttle, this is what it would look like. Now, it's not trying that we're saying we want to advocate putting this on the shuttle, far from it. What we're trying to do is trying to show you how this capability may work in the future as we go into even not just aeronautics domains, but as we move into the exploration domains. And so we needed reentry data from the standpoint of very high-speed movement and also trying to look at very large fields of regard. So if we can run this, I'll show you what this looks like. It's going to it's a playback of, again, STS